So we are going to see the applications of electronegativities now. This is another important area. The first application is a calculation of a partial ionic character of a covalent bond. See, the covalent bonds are not purely covalent. They have a partial ionic character just because of the electronegativity differences. So when the electronegativity differences are there, what will happen? The shared pair of electrons, they are not at the middle or at the center point. They are shifted towards any one of the atoms. So that atom towards which the electron density is shifted will have a partial negative charge, and the other atom will possess a partial positive charge. So because of that, a minute polarity will be induced, and the polar nature is nothing but the ionic nature. So the partial ionic character is caused by the difference in electronegativities, which can be calculated by the empirical formula proposed by the Pauling, which is 1 minus e power minus 0.25 chi a minus chi b into 100, where chi a and chi b are the electronegativities of the atoms A and B in the molecule. So the same formula is further simplified by Pauling, and which was given as the percentage of ionic character is equal to 18 into chi a minus chi b to the power 1.4. So for the hydrogen fluoride, the ionic character found was a 44.12%. By the Pauling's formula, it was found out to be 43%, almost equal. So which says that the formula is almost correct. Look here, the hydrogen fluoride is not a purely ionic and all purely covalent, which possesses 44.12% of ionic character. So the remaining is the covalent character. So the shifting of the electrons, if the electron is completely shifted from one atom to the other, it becomes 100% ionic. If the electron is shifted to a smaller extent, it becomes less ionic. So the percentage of ionic character of a covalent bond depends upon the electronegativity difference between the atoms forming the compound. And the second application is the calculation of enthalpy of a formation. What is this enthalpy of a formation? So it is the change of enthalpy during the formation of 1 mole of the substance from its constituent elements with all substances in their standard state. So for example, I want to form a water molecule. I take oxygen in gaseous state, which is the standard state of oxygen element, and I take a hydrogen in gaseous state, which is the standard state of the hydrogen, and I take these two gases and I want to jet them together and I want to form water molecule. What is the energy released, or what is the energy change accompanying this particular process of forming the water molecule? That is called enthalpy of a formation. Actually, the calculation of enthalpy of a formation is not at all possible. It is very difficult. Suppose if I give you some 6 hydrogen atoms and 12 oxygen atoms and 12 hydrogen atoms and 7 oxygen atoms, you will not be able to construct a glucose molecule. It is not possible at all. You will not be able to construct a glucose molecule from the constituent elements. It is only the plants can do this business. So formation is simply, it is a theoretically we are speaking that atoms can be taken and can be kept in order to form a particular molecule. It is not at all possible. If it is possible, then we can take a carbon, hydrogen, oxygen, nitrogen. We can make amino acids. If you are able to make amino acids and you can make DNA strands, if you are able to make DNA strands, you can make even living organisms by yourself with the elements, which is not at all possible. But chemically, we can calculate the enthalpy of a formation in an indirect manner. And one of the indirect manners which is available in the literature is the calculation of enthalpy of formation using the electronegativities, where the enthalpy of formation delta HF is equal to 23 E or epsilon. I can say it is chi A minus chi B whole square minus 55.4 NZ minus 26.0 N0. See, the NZ is the number of nitrogen atoms present in the compound for which the enthalpy of formation is calculated, and NO is the number of oxygens present in the same compound, whereas epsilon gives you the number of bonds. What are the total number of bonds? See, actually the enthalpy of formation is just the reverse of enthalpy of destruction. That is the bond breaking. What is the total energy spent to break all the bonds to get the elements back? Just the reverse of that is enthalpy of formation. So epsilon is number of bonds. So HCl, if you take HCl, number of bonds is only 1. If you take BeCl2, number of bonds is 2. So here, if for BeCl2, the chi of Be, that is the electronegativity of beryllium, is 3.05. And the electronegativity of chlorine is 1.50. So as a model calculation, delta HF is equal to 23 multiplied by 2, because there are 2 bonds, beryllium to chlorine and beryllium to chlorine on the other side. There are 2 bonds, and the chi A is 3.05 and chi B is 1.5, so whole square, and minus, there is no nitrogen atoms, there is no oxygen atoms, those 0, 0. So when you do this, it comes around 103.5 kilocalorie per mole. So this is how the enthalpy of formation is calculated. And another application is measurement of bond length. See, bond length can be calculated. See, it is not the radius of one atom and the other atom, simply the summing up of these two radii will give you the bond length. No, that is not the understanding. Because depending upon the electronegativity, the nuclei can come closer. So greater the polarity, shorter is the bond. When the electronegativity difference is more, polarity is also more, so the bond is shorter. So this calculation was done by Shoemaker and Stevenson. So they wanted to find out the distance between the A and B. So the distance between A and B is equal to the atomic radius of A, atomic radius of B, minus 0.09 chi A minus chi B. That is the electronegativity difference. So when you substitute the appropriate values, see, for nitrogen oxide, NO, nitrogen atomic radius is 0.75, oxygen atomic radius is 0.74 minus 0.09. The electronegativity of nitrogen is 3.5, electronegativity of oxygen is 3.0. So you are getting 1.445 angstrom unit. The experimental determination shows it is 1.46 angstrom unit. Therefore, it is almost equal. So the proposed equation is almost accurate. Similarly, the bond distance, bond length can be calculated for carbon and oxygen, which is 0.77, the atomic radius of carbon, and 0.74, the atomic radius of oxygen, minus 0.09 into 3.5 minus 2.5. So it is 1.42 is the distance. Now look here. Another thing is explanation of bond angles. Explanation of bond angles can also be obtained from the electronegativity studies. So in the case of polyatomic molecules, what about the electronegativity of the central atom? So this is the central atom, nitrogen, phosphorus, arsenic, antimony. So central atom. If the electronegativity of the central atom is highest, then what will happen? There will be more repulsion between the lone pair and the bond pair, because bond pairs are also brought closer to the lone pair. So the bond pair lone pair interaction will be more if the electronegativity of the central atom is higher. So in NF3, as the electronegativity of nitrogen is 3.0, the bond angle is 1.2, sorry, 102 degree. In the case of PF3, the electronegativity of phosphorus is 2.1, the bond angle is 97 degree. In the case of arsenic, it is 2.0, so 96 degree. In the case of antimony, it is 1.9, so 88 degree. So the electronegativity of the central atom, it attracts the shared pair of electrons towards itself. So because of the bond pair lone pair interaction, Bond pair lone pair interaction, the bond angle is higher for the central atom with a higher magnitude of electronegativity. And the last application, I think, it is in the proposal of reaction mechanism. There is application of electronegativity. Sometimes we may not understand what happens in the reaction. This is the reaction which we have already seen. Look here, methyl iodide plus the complex sodium plus MnCO4 minus the complex carbon monoxide manganese complex. When this is reacting, you are getting sodium iodide. This CH3 is substituted here, CH3MnCO5. The mechanism is, look here, the carbon is here, CH3 is there, I is there. Comparing the electronegativity of a carbon and iodine, iodine is delta minus, more electronegative than carbon. So carbon becomes delta plus. So what happens? This iodine, it goes along with the sodium to become sodium iodide. And then this minus charge attracts this plus charge, and what is formed is a CH3MnCO5 complex. If fluorine is present in the place of hydrogen, what will happen? The carbon would have become delta minus, iodine would have become delta plus. In such cases, what will happen? The sodium plus will go towards this carbon. This iodine plus will be attracted by MnCO5 minus. So what is formed is, this is iodine and sodium combines to form sodium iodide, right? And then this MnCO5 minus combines with the iodine to form MnCO5 I minus, and then this CF3 becomes a dimer. Two molecules of CF3 will combine to form C2F6. So the entire reaction mechanism is changed because of the electronegativity of the carbon. But the electronegativity of the carbon is determined by the atoms attached to this carbon because of the chemical environment. Similarly, look here, HOCl is acid because the chlorine is with +1 charge. So what happens? This +1 charge, it attracts the oxygen, and then the hydrogen goes out as a H+. But BOH twice is a base because the electronegativity of beryllium is less than oxygen. Therefore, what happens? Whether the H+ wants to go, it has to go along with its O. So OH group comes out. So in the case of HOCl, H+ comes out. In the case of BOH twice, OH group comes out. It all because of electronegativity. So the reaction mechanism can be explained with the help of electronegativity. Next one, the diagonal relationship. See, the electronegativity, when you move along the period, increases, down the group decreases. So if you move along the diagonal, it will almost remain the same, because one step further increases, one step down decreases. So here it has increased, here it has decreased. So the lithium and the magnesium, they show almost equal electronegativity, and because of that, lithium and magnesium show diagonal relationship. Their chemical behaviors are identical. And another thing, types of bonds can be found out using the application of electronegativities. If electronegativity difference is 0 or small, the bond will be covalent. If it exceeds 2.5, the bond will be electrovalent. So 2.5 can be fixed at the middle, and less than 2.5, the bond will be covalent, and greater than 2.5, the bond will be ionic. So these are all the applications of electronegativity.